Download this code from codegive.com, link in the description below. OK, let's dive into a detailed explanation of using a buffer overflow to call a function named reverse in C. This is a classic exploit technique, and understanding it is crucial for both offensive and defensive security perspectives. We'll cover the concepts, the C code, the exploitation steps, and some safety considerations. Disclaimer: this tutorial is for educational purposes only. Exploiting buffer overflows without authorization is illegal and unethical. Use this knowledge to understand vulnerabilities and develop secure software. 1. Understanding buffer overflows. The core problem a buffer overflow occurs when a program writes data beyond the allocated memory region for a buffer. In C, and some other languages, there are no built-in bounds checks on array or buffer access. This means you can write past the end of an array or a char buffer without the compiler or runtime system stopping you immediately. The vulnerability the lack of bounds checking opens the door to malicious attacks. If an attacker can control the data written to the buffer and the location it's written to, they can overwrite critical data, like return addresses on the stack. Stack-based buffer overflows. The most common target for buffer overflows is the call stack. When a function is called, a stack frame is created on the stack. This frame contains local variables the variables declared within the function. Function arguments the values passed to the function. Return address the address in the caller function to which execution will return after the called function completes. Frame pointer, EBP/RBP, a pointer to the base of the previous stack frame, used for debugging and stack unwinding. The attack the attacker's goal is to overwrite the return address on the stack with the address of the function they want to execute, in our case, reverse. When the vulnerable function returns, instead of returning to its original caller, it jumps to the address the attacker planted on the stack, the reverse function. 2. Example C code, vulnerable program. Explanation reverse, char str, this is the function we want to execute via the buffer overflow. It takes a string as input and reverses it in place. It then prints the reversed string and exits. We exit here because the stack is corrupted, and attempting to return will most likely crash the program. Vulnerable function, char input, this function contains the buffer overflow vulnerability. Char buffer 32, a character buffer of 32 bytes is allocated on the stack. strcpy, buffer, input, the strcpy function copies the string pointed to by input to the buffer. This is where the vulnerability lies. strcpy does not perform any bounds checking. If input is larger than 31 bytes, plus the null terminator, strcpy will write past the end of buffer and overwrite other data on the stack. Main, int argc, char argv, the main function receives command line arguments. It checks if an input string is provided. If so, it calls vulnerable function with the input string. 3. Exploitation steps. Here's a breakdown of the steps involved in exploiting this buffer overflow. We'll use a combination of analysis and crafting a specific input string. Step 1, compilation. Compile the C code. It's essential to disable stack protection and address space layout randomization, ASLR, for this example to work reliably on most modern systems. These security measures make exploitation more difficult. Note that disabling these protections makes the system significantly more vulnerable in real-world scenarios. No stack protector, disables stack protection, example stack canaries. *Z exec stack, marks the stack as executable, needed if you were injecting shellcode, which we are not doing here. *no pi, disables position independent executable, pi, which means the base address of the executable will be the same every time it runs. This is crucial for our exploit because we need to know the exact address of the reverse function. Step 2, find the address of reverse. We need to determine the memory address where the reverse function is located. We can use GDB, GNU Debugger, or objdump to find this. Using GDB *. 1. Start GDB with the executable, gdb/overflow. 2. Set a breakpoint at the beginning of reverse, optional, but helpful for verification break reverse. 3. Run the program, run AAAA, provide any argument to run the program. 4. Print the address of reverse, print reverse. 5. You'll see output similar to $1 equals void, char asterisk, 0x0005555555555169 reverse, the address 0x0005555555555169 will likely be different on your system. Using objdump asterisk. This command will output a line that includes the address of reverse. For example, again, the address 00000000000001169 will probably be different on your machine. The actual address will be displayed before the G character. Important note: if you did not compile with no pi, the address will be relative to the base address of the executable, which can change with each execution. Step 3, determine the offset to the return address. We need to figure out how many bytes we need to write to the buffer to overwrite the return address on the stack. We can use GDB for this as well. 1. Start GDB with the executable, gdb/overflow. 2. Set a breakpoint in vulnerable_function before strcpy, break vulnerable_function. 3. Run the program with a long input, run For continue execution until the breakpoint is hit, c. 5. Examine the stack, x/32gx$rsp, this command displays 32 giant words, 8 bytes each on a 64-bit system, from the stack pointer, $rsp. You can adjust the 32 as needed. Look at the output. You'll see a bunch of memory addresses. We're interested in finding where our AS 0x4141414141414141 in hex, start overwriting values. Look for the saved return address, the address of where main will return after vulnerable_function. By counting the number of AS you need to write before overwriting this address, you determine the offset. Alternatively, you can set a breakpoint after the strcpy call and examine the stack. This might be slightly easier. On a 64-bit system, the return address will typically be 8 bytes. Experiment with different input lengths until you precisely overwrite the return address. For instance, if you find that after 40 AS you start seeing AS in the return address location, the offset is 40. Step 4, craft the exploit payload. Now that we know the address of reverse and the offset to the return address, we can create the exploit payload. Padding create a string of A characters with the length of the offset we found in step 3. This will fill the buffer and overwrite the stack up to the return address. Asterisk address of reverse asterisk append the address of the reverse function to the padding. This is the address we found in step 2. Asterisk important asterisk you need to write this address in the correct byte order, little endian or big endian, for your system's architecture. Most systems are little endian, meaning the least significant byte comes first. For example, if reverse is at 0x000055555555555169 and the system is little endian, you would write the bytes \x69 \x51 \x55 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 \x00 \x00 \x00. Asterisk for testing, use \x90 for the padding. \x90 is the opcode for the NOP instruction, no operation. Asterisk example, assuming little endian, offset of 40, and reverse at 0x0000555555555169. Asterisk step 5, run the exploit. 1. Save the Python script, example exploit.py. 2. Make the script executable, mod plus x exploit.py. 3. Run the exploit and pipe the output as input to the vulnerable program. Asterisk expected result asterisk. The program should not print program completed normally. Instead, it should print reversed string, followed by the reversed version of the padding you provided, the AS. Then the program will exit. This confirms that you successfully overwrote the return address and executed the reverse function. 4. Important considerations and troubleshooting. Asterisk endian asterisk pay very close attention to endian, little endian versus big endian. If you get the endian wrong, the program will likely crash with a segmentation fault when it tries to jump to an invalid address. Asterisk address space layout randomization, ASLR randomizes the base addresses of libraries and the executable in memory. This makes it more difficult to predict the address of reverse. For the exploit to work, we disabled ASLR by compiling with no pi. Asterisk stack protection, stack canaries are random values placed on the stack before the return address. If the stack is overflowed, the canary will be overwritten. The program checks the canary before returning, and if it has been changed, the program will terminate to prevent exploitation. We disabled stack protection by compiling with no stack protector. Asterisk executable stack asterisk some systems disable executing code directly from the stack for security reasons. To get around this, we compiled with z-execstack. However, this option is generally considered insecure, and it's better to find other techniques to bypass this protection, example return-oriented programming, ROP. Asterisk debugger, GDB. The debugger is your best friend. Use it to examine the stack, set breakpoints, and step through the code to understand what's happening. Asterisk 64-bit versus 32-bit asterisk the size of addresses and the stack layout differ between 32-bit and 64-bit architectures. The examples here assume a 64-bit system. Asterisk compiler optimizations can sometimes change the stack layout or eliminate vulnerabilities entirely. Compile without optimizations, O0, for easier debugging. Asterisk system differences memory addresses and stack layouts can vary slightly between different operating systems and even different versions of the same operating system. You might need to adjust the offset or address based on your specific environment. Asterisk null bytes asterisk the strcpy function stops copying when it encounters a null byte, \x00. If your reverse address contains a null byte, strcpy will stop copying before overwriting the entire return address. You can work around this by using alternative functions that don't stop at null bytes, example mempy, or by finding a different function to call that has an address without null bytes. Non-executable stack *. Many modern systems mark the stack as non-executable by default. Attempting to jump to shell code placed on the stack will result in a crash. This protection can be bypassed using techniques such as return-oriented programming, ROP. 5. Mitigation techniques, how to prevent buffer overflows. Use safe string functions *. Avoid strcpy, sprintf, gets, and other functions that don't perform bounds checking. Use strncpy, tinprintf, fgets, and other safer alternatives that allow you to specify the maximum number of bytes to copy. Bounds checking *. Always check the size of the input against the size of the buffer before copying data. Stack protection, canaries enable stack canaries, usually enabled by default in modern compilers. Address space layout randomization, ASLR enable ASLR, usually enabled by default. Data execution prevention, DEP, /no execute, NX enable DEP/NX to prevent execution of code from memory regions that are not marked as executable, example the stack. Use memory safe languages. Languages like Rust and Go have built-in memory safety features that make buffer overflows much less common. Code reviews and static analysis. Thorough code reviews and static analysis tools can help identify potential buffer overflow vulnerabilities. Address sanitizer, ASAN, a powerful tool that detects various memory errors, including buffer overflows, at runtime. Compile with fsanitize equals address. 6. Return-oriented programming, ROP. While this example directly calls the reverse function, a more general and powerful exploitation technique is return-oriented programming, ROP. ROP is used to bypass DEP/NX. How ROP works *. Instead of injecting shell code onto the stack, ROP involves chaining together small snippets of existing code, called gadgets, that end in a RET instruction. By carefully placing the addresses of these gadgets on the stack, you can control the execution flow of the program to perform arbitrary actions. ROP gadgets. ROP gadgets are typically short sequences of instructions that perform a simple operation, example moving a value from a register to memory, followed by a RET instruction. ROP chain. A ROP chain is a sequence of gadget addresses on the stack. When the vulnerable function returns, it will execute the first gadget, then the RET instruction in that gadget will cause it to jump to the address of the next gadget, and so on. 7. Conclusion. Buffer overflows are a serious vulnerability that can allow attackers to take complete control of a system. By understanding how they work, you can develop more secure software and better protect your systems from attack. Remember to always use safe string functions, perform bounds checking, and enable security features like stack protection and ASLR. This tutorial should have given you a solid foundation for exploring this complex topic further. Good luck, and happy, safe, hacking.